All right, ladies and gentlemen, let's continue on with combustion here, reacting systems. So last time we calculated the heat rejection by burning propane stoichiometrically in a combustor. Today we're going to solve, and that problem was relatively easy to do because we knew the exit temperature. We knew the product temperature. TB in that case was 500 degrees Kelvin. So we could immediately calculate the specific enthalpies for all components at the outlet as well as the inlet. So that was a relatively easy problem to do. Let's do a slightly harder problem today. Instead of having a heat transfer with a known exit temperature at the combustor, instead we're going to insulate the combustor. So the combustor is a channel, a duct. We're going to mix the air and the fuel together. We're going to burn it, but we're going to wrap the duct and the combustor with insulation. So we're going to set Q dot equal to 0. No heat transfer. We're going to wrap it up in insulation. So all that heat is released and results in a temperature increase, very large temperature increase of the mixture, producing very hot product or exhaust gases. So the idea here is insulate the combustor, same mass flow rates as before, but now we want to know what the exit temperature is. What is the exit temperature, TB, or the outlet temperature? So that's the plan for today. So let's continue on here and write the energy balance. So let's write the energy balance here. So I'm running out of chalk. Let's see here. Let's see if I got some additional chalk. Getting a little low. Let's see here. So analysis. So let's write the energy balance here. Q dot, no work, steady state. We have 2 inlet flows and we have 3 outlet flows. So I'm just going to immediately go to the energy balance. Let's see here. Q dot, the sum of the N dot H outs. So I'm going to write N dot CO2 H bar, and that is evaluated at the product state, B. And then I have N dot H2O, H bar, and that is for the outlets. Hold on a minute. Make sure my notation's a little bit better here. So N dot H bar, and that's going to be for the CO2 at the outlet or the product side. And then I have N dot H bar, and that's for the H2O evaluated at the outlet. That's on the product side. And then I have plus N dot H bar for the nitrogen, which doesn't participate in the reaction, so it doesn't get burned up. And that is evaluated at the outlet as well. And then I have the inlet flows. So I have minus N dot C3H8, H bar, C3H8 evaluated at the inlet or the reactant side, plus N dot H bar, and that's for the O2 component, evaluated at the inlet, plus N dot, N dot H bar, the nitrogen, evaluated at the inlet. Okay? So that is our energy balance, Now let's expand some of these H bars here. So the H bar for the CO2, that's going to be equal to, that's the absolute enthalpy of the H2O evaluated at the exit temperature. In other words, it's the enthalpy of formation bar plus H bar evaluated at TB minus H bar evaluated at Tref. Okay, so that's the term for the CO2. That's the CO2 outlet specific enthalpy term. Okay, that's for the CO2. CO2. The H bar for the H2, same thing. H bar sub F, H bar evaluated at TB minus H bar evaluated at Tref. And again, that's for the H2O. Okay, that's for the H2O at the outlet, The nitrogen, so that's the enthalpy of formation for the nitrogen plus H bar for the nitrogen evaluated at TB minus H bar evaluated at Tref. And again, that's for the nitrogen. The inlet enthalpy, specific enthalpy, well, so the temperature at the inlet was at the reference temperature, as you recall. So the inlet temperature was at the reference temperature, so all the enthalpies, specific enthalpies, are the enthalpies of formation in the energy balance. So H bar of the C3H8 evaluated at TA equal Tref, that's equal to the enthalpy of formation for the propane. Same thing for the O2. This is the enthalpy of formation of O2 because we're at the reference temperature at the inlet, and so is H bar for the nitrogen at the inlet. It's the enthalpy of formation for the nitrogen. Now, as you recall from last time, the H naught subs Fs for the oxygen and the nitrogen are 0. So this is 0. This is 0. And by the way, nitrogen, this term is 0 too. Okay? So these guys go away. These terms go away. So let's write out what we got. Let's write out what we got. N dot H naught sub F plus H bar at TB minus H bar at Tref. And this is for the CO2. That's for the CO2. Plus, same thing for the H2O. Now this term here, I have an N dot for the nitrogen. So I have plus N dot for the nitrogen. The enthalpy of formation is 0 for the nitrogen, so all I have is H bar evaluated at TB minus H bar evaluated at Tref, and that is for the nitrogen. Okay, that's the outlet enthalpy of the nitrogen term. And then I've got the last term here, which is the enthalpy of formation, or the specific enthalpy for the fuel. That's right here. So I get minus N dot enthalpy of formation, and this is for the propane. This is for the propane, okay? Now let's look and see what we know in this. I guess I'll write the H2O term out. So N dot enthalpy of formation plus H bar at TB minus H bar at Tref, and that's for the O2, H2O, water vapor, okay? Okay, so let's look and see what we know here. What do we know? We know the N dots for the fuel, for the nitrogen, for the H2O, for the CO2. We have all the N dots. We have all the N dots, so we got all that. We also know or can look up the enthalpy of formations. We can look up the enthalpy of formations for the O2, the CO2, the water vapor, and the fuel. So let's write what those are. Let's see here. Where's a good place to write this stuff? Let's go over here. Let's go over here and write down some of the properties. So the enthalpy of formation for the fuel, the CO2, and the H2O. Let's make sure we write those down. So enthalpy of formation for the propane. That's from a table. We already looked that up before doing the previous problem, but let's write it up one more time. Let's see here. The enthalpy of formation for the fuel is negative 103.8. And that's going to be megajoules per kilomole. Megajoules per kilomole. Let's show you again where that comes from. So we go to B13. Propane, negative 103.85, or if you like, and that's in kilojoules per kilomole, or if you like, 103.8 megajoules per kilomole. 103.8 megajoules per kilomole, okay? And the enthalpy of formation for CO2, for the CO2, let's see here, that is 393, negative 393.5 megajoules per kilomole. And the enthalpy of formation for H2O, enthalpy formation for H2O is 241.8, negative 241.8 megajoules per kilomole. Okay, so I looked those up all out of the table. So I got these enthalpies of formation now. H naught sub F for the CO2, H naught sub F for the H2O, and H naught sub F for the C for the propane. Okay, so I got those now. Now I'm trying to find TB, the outlet temperature. The H bars evaluated at TB are the only terms that are a function of the outlet temperature. So right now I need to get, so what else do I need? If I can get everything in this equation fixed, and I know the heat transfer is 0, it's adiabatic. I know this is 0, it's adiabatic. Then I'll have a single equation which is only a function of quantities which themselves are a function of the outlet temperature. It'll be a nonlinear equation, but nevertheless, let me get the H bar at T refs. Let me get all those. Let me get all those. H bar at T ref. Let's do this for, let's do it for the CO2. That's 9.3. Let's do for the CO2 at T ref, which is 298 Kelvin. That's 9.3, actually 9.4 kilojoules per, megajoules per kilomole. And H bar for the CO2 evaluated at T ref, that is 9.9 megajoules per kilomole. Okay, so now I have the H, and I need the nitrogen too. H bar for the nitrogen, N2, evaluated at the reference temperature. Let's do the nitrogen. The nitrogen, I'm looking for it here, 8.67 megajoules per kilomole. So these are all from table B12, and these are from B13. B12 and B13. Oops, damn, I'm sorry. Just wrote the enthalpies, specific enthalpies at the reference temperature out of table B12. So B12, 298. Let's see, CO2, 9.4 megajoules per kilomole. H2O, 9.9 megajoules per kilomole. And nitrogen, 8.6 kilojoules per kilomole. Okay, 8.6. I guess I have 8.67. I'll round that up to 8.7. Let's just do that. 8.7 megajoules per kilomole. Okay, 8.7. Okay, so now I have the enthalpies at the reference values. Okay, so now in this equation, I have the hrefs 2. So all I now have is a bunch of enthalpies evaluated at the exit temperature TB. The rest of the stuff is known. The rest of the stuff is known. Okay, how are we going to solve this? Well, we're going to solve it iteratively. We're going to do a guess and a check, but we're going to try to do it intelligently. Let's do a guess and a check and try to do it intelligently. I'm going to take everything on this equation that involves a known, take everything that involves a known in that equation and put it on the right-hand side, and everything that involves TB, I'm going to put on the left-hand side. So all this is equal to 0. So I'm going to take everything that is known and put it on the right-hand side and leave everything that is unknown on the left. So on the left, I have n dot H. This is for the CO2. N dot CO2, H bar CO2 evaluated at TB. Okay, so this is this term now. I'm going to get rid of these checks because I got to make sure I'm doing this all right. I'm going to be checking them off as I rewrite the equation. Okay, so CO2 H bar, okay, I got that. Plus N dot H2O H bar H2O evaluated at TB plus, so that's this term right here. And then I got the nitrogen term, N dot nitrogen H bar evaluated at TB. So that's this term right here, check. And I'm going to call all of this, all these terms, the left-hand side equation. Left-hand side. So that's everything that is a function of the outlet temperature. Left-hand side. What about the right-hand side? Right-hand side. Well, the right-hand side, so I'm going to take the N dot for the CO2, the H naught sub F, and the H ref term. So I'm going to get N dot CO2, H naught sub F for the CO2 minus H bar for the CO2 evaluated at T ref. So that takes care of this term and this term. Plus N dot H2O, H naught sub F for the H2O minus H bar for the H2O evaluated at the reference temperature. So that takes care of this term and this term. And then I've got plus N dot N2 H bar of the N2 evaluated at Tref. So that takes care of this term. And then I have a plus. Oh, I guess I need to put some negative signs in front of all this stuff. Let's see. So those terms are being moved over onto the right-hand side. So let's see here. So this needs to have a negative sign in front of it. This needs to have a negative sign in front of it. This already has a negative sign in front of it, so that becomes a positive. And then I have a negative. I move it over to the right-hand side. It becomes a positive. N dot C3H8 H enthalpy of formation for the C3H8. Okay? All right, so everything I know in that equation, I know the N dots, I know the enthalpies of formation, and I know the enthalpies evaluated at the reference temperature. So I plug in all my enthalpies that I know. Enthalpies of formation, enthalpies evaluated at Tref along with the N dots, and I get 1137.4 megawatts. 1137.4 megawatts. 1134.7 megawatts. So the right-hand side equals 1134.7 megawatts. Now, when I have the right outlet temperature, the right-hand side should be equal to the left-hand side. So let's make a table and let's guess some temperatures at the outlet, calculate the left-hand side, and see if it equals the right-hand side. So let me make sure everybody's on the same page. The E balance has been rewritten. And so it says left-hand side equals right-hand side. This is just the E balance I've rewritten with the unknown terms on the left and the known terms on the right. So that's what the E balance can be rewritten as. All right, so let's make a little table. I'm going to have temperature at the outlet here in Kelvin, and I'm going to have the value of the left-hand side, and that's going to be in megawatts. Okay. Now I'm going to choose some temperatures here. I'm going to choose 1,000, 2,000, 2,400, and 2,500 degrees. So 1,000, 2,000, 2,400, and 2,500 degrees Kelvin. 4 different temperatures, okay? And I'm going to calculate the left-hand side for each of these 4 temperatures, okay? All right, I'm not really interested in the right-hand side equation anymore, so let's do a sample calculation for a left-hand side at, let's say, 1,000 degrees. How about we do 1,000 degrees here? Let's see here. So let's get the book. So N dot CO2, H2O, and N2, let's see, they are 1.5, 2, and what, 9 point something, 9.4, so I know those. Let me calculate the H bars at 1,000 degrees. Let's do it for the CO2. Let's do it for the CO2. And let's do the H2O. And let's do the nitrogen. Okay, let's get these things. All right, 1,000 degrees. 1,000 degrees. There's 990,000. There's 1,000. CO2, H bar, 42 and megajoules, so 42.8. 42.8 megajoules per kilomole. 42.8. For the water vapor. Water vapor. 35.9. 35.9. 35.9 megajoules per kilomole. And for the nitrogen, it's the last column. For the nitrogen, 30.1 megajoules per kilomole. 30.1 megajoules per kilomole. Okay, so now I have all my H bars evaluated at my assumed outlet temperature of 1,000 degrees. Let's plug into the left-hand side equation. Let's see here. So for 1,000 degrees, let's see here. Guess TB equals 1,000 degrees. So that means the left-hand side in that case, let's see, n dot CO2 is 1.5 kilomoles per second, and the H bar for the CO2 is 42.8. All these are going to have units of megawatts, so I'm going to have units of megawatts, megajoules per kilomole, and kilomole per second, so megawatts. And then I have two, this is going to be the H2O, 35.9, and then I have 9.4 kilomole per second for the N dot for the N2, and then I have 30.1 megajoules per kilomole. Let's crank this all out and see what we get. Let's crank this out and see what we get. Let's see here, 1.5 times 42.8 plus 2 times 35 plus 9.5 times 30. And I get 420. 420 megawatts. So if I assume an outlet temperature, of 1,000 degrees, it's not the right temperature, but if I assume a temperature of 1,000 degrees, then the left-hand side terms sum up to 420 megawatts. And if the energy balance is satisfied, in other words, the left-hand side equals the right-hand side, then the left-hand side better be equal to 1134.7 megawatts. I'm not anywhere near that. I'm at a low value for the left-hand side. Now, specific enthalpy goes up with temperature, so the left-hand side is too low. So clearly, I need to increase the outlet temperature, TB. So why don't I increase it to 2,000? And I re-look up H bar for all the outlet quantities, and I get 918 for the left-hand side at 2,000 degrees. 918. Getting a lot closer. Getting a lot closer. Let's crank it up to 2400. And I get 1140 for the left-hand side. 1140 for the left-hand side. Let's say I want to crank it up just a bit more. For 2500, I have 1194. 1194. So clearly 2500 overshoots the temperature, and 2400 is just about right. 2400 gives, so 1140 is approximately 1134. So that tells me TB is approximately equal to 2400 degrees Kelvin. Okay? TB is approximately 2400 degrees Kelvin. TB, approximately 2400 degrees. And let's put that in our schematic too. Let's put that in our schematic. Approximately 2400. That's really hot. But as far as combustor temperatures go, that's pretty normal. Most combustion chambers, 2000, 1800, 2400. Most combustion chambers obviously aren't perfectly insulated. In fact, they're usually not running stoichiometric either. The more air we put in there compared to the fuel, the leaner the mixture, the cooler the outlet temperature will be. So a lot of combustion chambers, most combustion chambers don't run stoichiometric. So the outlet temperature, TB, is liable to be a lot lower than the maximum temperature, which is what we see here. Okay, so the name we give to this particular outlet temperature under this particular set of conditions, we have stoichiometric combustion, insulated. So for stoichiometric combustion, where the intake, TA, which is T reactants, is equal to the reference temperature, and Q dot is equal to 0. So we're insulated. Insulated combustion chamber. Under these conditions here, that outlet temperature, TB, has a particular name. TB is renamed the adiabatic flame temperature. Adiabatic. Adiabatic because there's no heat transfer. T adiabatic is equal to TB. Adiabatic flame temperature. Adiabatic flame temperature. Flame temperature. The temperature of the exhaust when there's no heat transfer, stoichiometric combustion, inlets are at the reference state. The outlet temperature is equal to the adiabatic flame temperature. That's what we call this outlet temperature. It is kind of a flame temperature. It's kind of a flame temperature. You stick a thermometer right here, right on the edge of the flame, it's going to be 2400 degrees. So that is a flame temperature. There's no heat transfer anywhere in here, so really that temperature is T adiabatic, and it's equal to TB. So right on the edge of the flame, you've got the adiabatic flame temperature. Now in real life, there's a little bit more going on here. Stuff that I don't want to discuss, you can wait till grad school. The temperature is liable to be a little bit lower in reality if you stick a thermometer right there. And the exit temperatures that you find on these adiabatic combustors is liable to be a little bit lower, period. There are reasons for it. But this is a good ballpark, a good rule of thumb for looking up the adiabatic flame temperature is a good approximation for how hot the exhaust is under stoichiometric conditions, complete combustion, where the inlet is at the reference state. Okay, get a good idea of what the flame temperature is. Not exact. In real life, the actual measured temperature there will be a little bit lower. There are reasons for that I don't want to go into. All right, so I think that's about it. One thing I do want to point out, you can also do the entropy balance on these reacting systems. I do have a section in the notes, on how this is done. It's really the same old thing. You know, once you've done the energy balance, you've evaluated entropy to include the chemical entropy, it's just the same old thing. I do have an example here in the notes. It's the last example in the textbook. It's the entropy generation due to combustion. So let's ask ourselves, you mix this fuel in this air, you light it with a spark or something, or a little flame holder, and it burns. That combustion process, is it reversible or irreversible? It happens spontaneously in nature. It's got to be irreversible. So there should be some entropy generation right in this thin little flame front. So the flame has a certain thickness. And right in here, we have a bunch of entropy being generated due to the irreversibility of the combustion or chemical reaction. So if you do an entropy balance on this thing, this combustor, you better get an S dot gen greater than 0, else the reaction cannot occur. If you have a reaction and you find out that S dot gen is negative, then in nature, the reaction doesn't go the way you think it goes. It goes the opposite way. So let's look here at an example involving entropy generation due to combustion. So here we have a similar problem. The flow rates are a little bit different. Still propane, stoichiometric. Let's see here. This is the inlets are all at some temperature, 25 degrees. You go through, apparently it's an adiabatic problem, so it's no heat transfer. So here's the entropy balance. Notice the entropy balance is written in terms of n dots. So solving for S dot gen, we have, so it's insulated, the inlet temperature is approximately is equal to the reference temperature. So the outlet temperature is going to be the adiabatic flame temperature. Okay, we already know that. So you're going to have entropy generation is equal to a bunch of differences between the outlet and the inlet specific entropy. The outlet specific entropy is going to be evaluated at the adiabatic flame temperature, and the inlet specific entropy is going to be evaluated at the inlet temperature. Okay. Now, one little thing here. So let's look at how you calculate the specific entropy for a particular component at the outlet. So here's your S of the N2 evaluated at the outlet temperature and the outlet pressure. Something to notice here. The outlet is a mixture. It's a mixture of nitrogen, carbon dioxide, and water vapor. So the pressures of each component are not equal to the outlet mixture pressure. They are partial pressures. So you look here and how to calculate S, including the chemical enthalpy. You see here that you have partial pressure of the N2 at the outlet. Here's P ref. Here's your S naught stuff. And then here's your S at the reference, which is the enthalpy of formation for the N2. The N2 has a 0 enthalpy of formation. The entropy of formation. Let's see here. What's the entropy of formation for, what page is this? The entropy of formation for nitrogen is 0.19 megajoules per kilomole degree in Kelvin. Okay? So that's what you plug in right here. And so is so there's the entropy of formation. There's the S naught at the reference temperature, which is also the entropy of formation. And then we have S naught evaluated at the adiabatic flame temperature, 2400, which turns out to be 0.25 megajoules per kilomole. All this stuff was had from tables. The partial pressure for the N2 at the outlet is the mole fraction of the N2 at the outlet times the mixture pressure. The mixture pressure is 1 atmosphere. This was assumed to be an isobaric combustor. So we go through and we know the N dots for the various quantities. So apparently 73% by moles of the outflow is nitrogen. And so you get a partial pressure about 0.73 atmospheres at the exit, the partial pressure for the nitrogen. Plugging in everything we know, we find out that the absolute entropy of the nitrogen at the exit is 0.261 megajoules per kilomole degree in Kelvin. A similar thing is done with the remaining CO2, the remaining H2O. And you plug in and you get S dot gen, and this is in per unit mole flow of the propane, is equal to 2.2 megajoules per kilomole degree in Kelvin of propane mole flow. Notice that this is positive, so this reaction is irreversible and will occur in nature. So the reaction we've been talking about results in entropy generation by the amount of 2.2 megajoules per kilomole of flow per degree in Kelvin. So this is a irreversible or spontaneous process and will occur in nature. So I do have an example here on entropy, applying the entropy balance to a reacting system. It's extremely tedious. It's probably take over an hour to do. You can look over the example here. It's just the same old stuff. So I'm going to leave it to you to have a look at how it's done. Take care, ladies and gentlemen.